What's going on, everyone? All right, so no matter where you are, I hope you are having an amazing morning, afternoon, evening, wherever you are. I hope things are going amazingly well for you. All right, so I'm hoping that you all know who I am by now, but I'm still going to put this in here for maybe some of you that have just jumped on. My name is Dr. Jason Dinsmore, and I'm known as the OChem Whisperer. And what I want to do is I want to help you discover your inner OChem rockstar, that part of you that already knows how to completely and totally crush organic chemistry. And I'm going to show you as we go through these lectures that you already have that inside of you. Now, what in the world are we going to be doing today? What we're going to cover in this lecture is essentially we're going to learn the three basic ways to draw molecules. We're going to find those three basic ways. I'm going to talk about them as expanded, condensed, line drawing, and then towards the end what we're also going to talk about, which is the key to organic chemistry, is understanding nucleophiles and electrophiles. All right, are you all just as excited as I am? Okay, fantastic. Let's dive in. Now, as I just said, there are three basic ways to draw organic chemistry molecules in your class, okay? There's the expanded form, which is kind of self-explanatory, right? It's going to be like stretched way out like this. There's going to be the condensed structure, which also is kind of self-explanatory. It kind of crunches down like this, really close. And then we're also going to talk about the line structures, which is the basic one that you've seen me draw in these lectures, all right? Now, like I said, this is going to be the big one that you are going to see throughout your organic chemistry career, whether you're only going to take OChem 1 or you're going to take OChem 2, or maybe you're deciding that you want to go on to graduate school, major in this, whatever that is. But this is the basic one because it takes up the least amount of space and it's the easiest to kind of draw and kind of explain what is happening, all right? So this is the expanded form, right? And it kind of makes sense. We can see that we're drawing everything. We've got all of our carbon-carbon bonds. We have all of our carbon-hydrogen bonds. We've got all these lines and letters literally showing anything and everything that is associated with this molecule. Now, you can imagine that if you had to draw every single structure on your organic chemistry exam or quiz, it would take forever, right? And there'd be no space left on your exam. So most professors will give you just a few examples of drawing these out just to make sure that you understand what to do. Now, the next one that's after this is we're going to condense things down. So what you're going to notice here, if you look, is we're going to take all the carbon-hydrogen bonds, we're going to condense that down. Instead of having all the bonds to hydrogen, we're going to write hydrogen with a subscript saying how many hydrogens are on each carbon. Now, this is what it's going to look like here. It's much, much easier to look at, right? And it doesn't take up as much space. So the way this works is you find the carbon and then the hydrogens right next door. It's got the H and then the subscript. That's telling you all those hydrogens are on that carbon. Rather than drawing out all the bonds, we're going to say, for example, we have CH subscript 3, so there's 3 hydrogens on that carbon that was before it. Okay, that's how it was. So we got CH3, CH2, CH2, CH3. Okay, but the key here to note is that you want to remember that this whole thing is based off of the carbon-carbon bonds. It's kind of like your carbon framework. So essentially in this case, the carbons are attached to each other. You don't read this as though the H subscript 3, that H3 is attached to the carbon. That's not what this is saying. It's saying that all of the carbons are attached to each other and then the hydrogens are coming off of each individual carbon based off of the hydrogens next to it, all right? Now, the next one, the one that I've been using is this. And a lot of students are like, what in the world is this? How does this even relate to what you were just showing me before? This doesn't make any sense, Jay. Like, what is that? Is that a lounge chair? Is that like a broken staircase? Like, what is that, right? So I'm going to show you. So the way to think about this is every endpoint, you see the endpoints, or you see a mountain or a valley or what I call kinks, those are where carbons are, okay? So there's a carbon at every single endpoint and a mountain or a valley or a kink, however you want to look at that. And so you can see here that there's no lines, there's no letters, so it can be very confusing. But what this is showing you is where the carbons are in your molecule, all right? So what I'm going to do here is before we get into the line drawings, we're going to do some examples to make sure that you're complete OChem rock stars at drawing these things out, is let's look at all 3 of them side by side. So if we were to walk through here, here's carbon 1 in every single one of them, okay? So we can see in every single case, that's a C, a carbon, with 3 hydrogens coming off of it, and then it's bound to another carbon. So we can see we're maintaining our 4 bonds to carbon. So we can see in the first one, we can see all of the bonds, right? In the middle one, our condensed form, we can see that it's a CH3, and we have to remember that those the carbons are attached to each other, so that's our 4th bond. When we go all the way to the right-hand side with the line, we have to remember that those endpoints are CH3 groups. Okay, that's a carbon. Now, if we systematically walk through here, here's going to be our 2nd carbon, here's our 3rd carbon, and here's our 4th carbon. So the line drawings we can see are basically telling us how many carbons are in there, and then we have to remember that carbon has 4 bonds to it, and that we're going to have the extra lines coming off. But we're going to do some examples here in a minute to kind of explain that, all right? Does this make sense? Is everybody feeling this? Does this make sense? Okay, cool. Awesome. Now, let's look at this. So I just want to kind of say this again because it's kind of important. The endpoints If you have a molecule and you see endpoints, whether it's up, down, left, right, whatever direction, you want to remember those are CH3 groups. It's a carbon with 3 hydrogens coming off it, okay? And if you had this, imagine we just did this infinitely long, we just did this like sideways staircase. The groups in the middle at the valleys and the peaks, whatever you want to call them, those are CH2 groups, a carbon with 2 hydrogens coming off it, okay? And like I said, we're going to do some examples to kind of show you this, all right? So let's say your professor gave you this molecule and said, I want you to draw the expanded or the condensed form. Let's walk through this and see what this looks like, okay? Let's look at the expanded form. So in this case, what I want you to do is when you have a structure like this, remember that all the endpoints or the kinks are where your carbons are. So what I want you to do is I want you to take this structure, and right now what I want you to do is I want you to draw this. So if you have a piece of paper, if you have a stylus, an iPad, whatever it is, some electronic device, I want you to draw this out. Okay, so draw the line. Then what I want you to do is look at all the endpoints and the kinks, and I want you to draw those, draw a C in every single one of those. So what I want you to do is take this, and right below it, I want you to draw this, where essentially you're drawing the letter C, which is a carbon, on all your endpoints and your kinks, your mountains and your valleys, okay? I want to go from there to here. Now, what we want to remember is now we have our carbon framework. Now we have to remember there has to be 4 bonds to every single carbon. So if we go all the way to the left-hand side, we can see that that only has 1 line coming off it, or 1 bond. So that means we need 3 other lines. So what we're now going to do is you can either do it below or on the same one. You want to draw those 3 lines, okay? So we went from the line drawing, we put our carbons in for our carbon structure, our framework. Now we're going to start adding all the bonds in there. Now what bonds do we make these to? In these structures, you've seen, for example, they're just a line, right? We don't see any letters, we just see lines. If you don't see any letters in there, you assume that the rest of the bonds are hydrogen. Okay, so in this case, we have 3 bonds here. What we're going to wind up doing is we have to put hydrogens on those. Okay, so there's our 4 bonds of carbon. Now what we're going to be doing is systematically doing the same thing on every single carbon. So if we go to the next one, we can see that that next carbon only has 2 bonds to it. So we have to add 2 bonds. If we go to the third one from the left, there's only 2 bonds, so we have to add 2 more, and then the last one we have to add 3. So we systematically now go in here and add all the rest of the bonds to hydrogen, okay? So take a minute just to kind of make sure the fact that what we did, just you're on the same page. We drew the carbon framework, then we started filling in the lines to make sure we have 4 lines or 4 bonds coming off to each one, and then we're going to add hydrogens because we don't have any lines, or we don't have any letters in the original structure we saw. Now, one other point I want to bring out, you don't have to draw your line drawings like this, which looks like kind of a lounge chair. You can actually take it, what's probably going to be easier is to draw it like this. So just count the number of carbons and draw all your carbons in a straight line, and then I think it's easier just to say, okay, I need 4 lines coming off of each one, or 4 bonds. Then you can just draw them very systematically and easily to get a structure like this, okay? Does that make sense? Does that sound good? Okay, cool, awesome. So let's look at this structure here now, okay? Now, I think you'd agree that the framework, the bottom part is exactly the same, but now we can see we've got something else on here. So we can think about this like a lounge chair, and that group coming off is like an umbrella, right? So we can see that now we do have letters. We can actually see letters here. So what we're going to do is we're going to do a very similar approach that what we just did. So the first thing we want to do is what? I'm going to ask you, what was the first thing we did when we had a structure like this? That's exactly right. We drew our carbon framework. So I want you to go in there, draw all of your carbons. We had a total of 4 carbons. We're going to draw those, okay? So go ahead and draw those. Then what we want to do is, and this is the extra thing that we didn't have last time, is I want you to go back to your structure and see what letters that you have that are not carbon and not hydrogen, okay? Now in this case, when I say not hydrogen, you can see that what I'm saying is when you have your carbon framework, I want you to look for the groups that are coming off, the group that is directly attached. That line is going directly to an O. If you see something that's not carbon, not hydrogen, I want you to draw it. So in this case, we're going to draw the whole OH because that's kind of a group as itself, okay? So now we go back and we can see that that's on the second carbon from the left. So we're going to add that in as well. So we've got our carbon framework, we put on our OH, and now what do you think we're going to do next? We're going to fill in everything else. We just look at this and figure out how many lines do we have to do off of each one of those to get our 4 bonds. So the first one on the left, we need 3 extra lines. On the second one with the OH, we need 1 extra line because we already have 3. If we go from third from the left, we need 2. And all the way on the right-hand side, we need 3. So if we fill those in, now we've got our expanded form. We have all of our bonds to carbon and everything is fine. All right? Pretty cool, right? Now what we want to do is we want to take this and we want to do this in the condensed form. So let's kind of see, we feel pretty comfortable with the expanded. Now let's do condensed. So remember the condensed form works like this. You take your carbon and you put your H beside your hydrogen and you have to put a subscript to say how many hydrogens you have, okay? So if we looked at the first carbon, we can see that would be a C and then we write an H and we've got 3 of them. So it'd be CH3. The next one with the OH, we don't have to worry about the OH, we leave it, but it's got 1 hydrogen. So the first one was CH3, the second one would be C just an H because we've got 1, And then if we went along, it'd be CH2 and CH3, and this is what it would look like, okay? So remember, we write our carbon, with our hydrogen subscript, and we're going to do that for each one. And then with our groups that are non-carbon or non-hydrogen, we're just going to write a line to them with it. So in this case, we've got our OH. So that's how we're going to go from, we're going to go from the line to the expanded to the condensed, okay? Cool. Now, this I wanted to show you is just kind of the whole process. This is how I want you to do this every single time so you can crush this in your class. The first step is the easiest. All you have to do is look at the molecule professor gave you, right? That's the easiest one to do, right? Then what we're going to do is we're going to go from the first structure. We're going to draw our carbon framework and any atoms that are not carbon or not hydrogen on there. So we can see we went from step 1 to step 2. We drew our carbon chain. Then step 3, we're going to fill in all the bonds with hydrogen, because if we don't see any other letters, then they have to be hydrogen. Those bonds are going to be to hydrogen, or lines are going to be to hydrogen. So in step 3, we just fill everything in. And then step 4, if we had to do the condensed, remember, we count the number of hydrogens. We write CH and then subscript down to get all that, okay? Pretty cool, right? You can actually use this step by step. So you can start using this in your class right now to kind of start crushing these if your professor's going to ask you these, okay? All right, so now, of course, you all knew this was coming, right? Now it's going to be your turn to draw some expanded and condensed structures. Now, I want to point out right now is that some of you might be thinking, well, Jay, you already gave us homework examples and you haven't given us the answers yet. I haven't forgotten about that, okay? I was trying to figure out if I was actually going to do because for those of you that aren't familiar with my Instagram page, I do a lot of times a whiteboard, so I actually work with the examples. I was debating if I was going to do that today or if I was going to do this one, and as you can see, I decided to do the PowerPoint. But I haven't forgot about it, so what I'm going to do is I'm going to create those and I'm going to post those as supplemental material. I told you all that I was going to post supplemental material periodically here and there that wasn't going to be live. Well, that's going to be that, and I'm also going to do it with these questions as well. But I need you to work on these because, for example, if you are not going to work with me one-on-one online tutoring like a lot of other students do, then I need you working these problems to make sure that you are going to be really prepared for your exam. So what I also want to explain like this is you might be saying, well, Jay, these are much different from the ones that you actually did, and there's a reason why I did that. One of the things that students tell me all the time is like, Jay, when I work with you or I'm working in my class, I feel pretty good about the examples. I do all the practice problems, all the practice exams, and I feel really good. Then I get into the exam and I have no idea what's going on. My professor puts all this stuff on there I've never seen before, and I don't know what to do. So what I'm trying to do is say, I'm going to show you the simple examples, and then I'm going to throw in there things that essentially we haven't seen in the simple examples and see how you do. Why am I doing this? Because what I've discovered over the many, many years I've been doing this is if you can do the simple examples, you can do anything that your professor throws at you, okay? So all you have to do is take that step-by-step process that I did and apply it to this. So you can see, for example, we didn't have a carbon chain with an oxygen in it in the first one. The middle one, we didn't have a carbon chain with a double bond. And in the last one, we didn't have a carbon chain with this double bond to an oxygen. But I know every single one of you can do that if you follow that step-by-step plan. I'm pretty sure some of you are already thinking, yeah, I think I do know how to do that. Yes, you do. Remember that. Do not doubt yourself. You do know how to do this. So go ahead and work on these, all right? Now, so what I want to do now is I want to show you how to go in the other direction. How we're going to go from this expanded to then down to a line drawn, okay? And these are the two things. Now, no matter which direction you're going from line to expanded or expanded to line, I always want you paying attention to your carbon chain. Where are all the carbons and how are they attached? So I'm going to highlight them right here, and we can see that on the left-hand side, we have 6 carbons, but they're all attached to each other. It's not a line, there's a ring, okay? And then the one on the right, we can see that we do have a kind of a line structure, but we have something now going up like this. So it's called a branching point. So you always want to, no matter which direction you're going into, focus on your carbon chain. So let's look at the one on the left. Now we can see that we have 6 carbons, they're in a ring, so essentially I want you to draw that, 6 carbons in a ring, okay? That's all we have to do. And pretty much you can see that that's basically a 6-sided shape. It's a shape and it's basically a hexagon, right? So we can already see the fact that that's what that's going to be, thinking about how we're going to draw the line. But first what we're going to do is the condensed. So we're going to draw our carbon framework. Then what we're going to do is we're going to draw any atom that's not carbon or not hydrogen, and we're going to condense everything down with like CH subscript. So I'm going to put this in right here. Now you'll notice in my example, this was just with the program. There's nothing wrong with the program. I think I just didn't figure out how to do this. On the top with the bromine, and I'm hoping you all saw that was a bromine, not a hydrogen, is I should have written CH with the line to the bromine. Okay, that's what you want to draw. I just couldn't for some reason get this program to do that. And if you go all the way to the bottom, that's supposed to be CH subscript 2 all together side by side. So that's what you want to do when you draw that. I just for some reason couldn't get it to work. But basically we want to essentially go from expanded to condensed. and we're doing the same process that we did before, kind of in reverse. So we find our carbon chain, and then we bring our H subscript, whatever the number is, okay? Now, if we're going to take this condensed and go all the way to the line, we can see that we've got 6 carbons, and it's going to look like this. So how do we go from the expanded? I think it's easiest to go from the expanded to condensed because we know what everything is. Sometimes it can be challenging to go from the expanded to the line because we have to get rid of all the letters, right, except the non-carbons and non-hydrogens. So this is what I want you to do when I want you thinking about this, is I want you to see how many carbons you have. So if I look at this, I'd say I have 6 carbons. They're in a ring. It's a shape, and essentially it's a hexagon. So draw a hexagon. And then we don't write hydrogens, we don't write carbons, we just write non-carbons and non-hydrogens. The only other thing is a bromine at the top, so you draw a line to the BR. See how simple it is? It's pretty cool, right? All right, so now let's look at the other example here. So here, once again, we don't get confused by all this stuff drawn everywhere. Draw your carbon framework and all non-carbon and non-hydrogen things. Okay, so first your carbon chain. And then, so we're going to draw that, not the hydrogens, and then we're going to just draw the carbon framework, and then we've got an OH on there. So we're going to draw that, okay? Now this time we're just going to go directly from the expanded to the line structure, okay? I'm just doing this just to get you familiar with how to go, from this, start to look at the carbon structure, and then go to line. But what you want to do here is once you've drawn this to go to the line, just imagine you erase every single carbon on there and just connect the lines. Watch. Boom, just like that. You see, it's like, I'll go back. You write the carbon framework and just imagine you didn't have the carbon framework there and you matched everything up. Boom, you get that. So you can see now the carbon framework is kind of like your platform, your foundation that's going to help you kind of work through these problems and go whichever direction you want to go, okay? So that's how to do that. It's pretty simple, right? No matter which way we go. So remember that step-by-step plan I showed you? You should be able to, now that I think about that, use that in any direction, whether it's line to expanded or expanded to line. So go ahead and try some examples, specifically the ones that I gave you, right? All right, so now, the last thing I want to talk about, if you all remembered, was nucleophiles and electrophiles. You're going to hear me talk about this so much that I'm hoping that all of you will be like, oh my gosh, you're talking about this again. I already know nucleophiles and electrophiles. And if you feel that way already, that is fantastic because that is the key to organic chemistry. And that means that you know it so well, it's like breathing or putting on your shoes and you're going to crush every example. Because if you understand this, that this reaction right here shows you every single reaction mechanism, every single reaction product that you have to predict, it's literally the key to organic chemistry. You can literally do anything in your class, all right? And so what we're going to talk about now is how to find your nucleophile and your electrophile, which is the biggest thing in organic chemistry, all right? So cool. So let's look at this example right here. Remember we talked about this in one of our previous lectures where we had the NC and we went through the whole Lewis structure and figured out why, like how do we build the C and the N together, that it's a triple bond, we have all these lone pairs, and the carbon is negative. If you didn't see that, go ahead and check out one of the previous lectures. But what I want to do here is I want to take this molecule and I want to actually put a hydrogen on there. I want to do this molecule instead of a negative charge. And the thing that we want to remember is every single line you see in organic chemistry is made up of 2 electrons, okay? And you're going to find this 2 is kind of an important thing. So we have 2 electrons or 2 dots per bond. We only need the 2 things to do a reaction, okay? So this 2, we're going to see this common thing over and over again. We only need a nucleophile and electrophile. And what I want to show you here is how you can take this and figure out nucleophiles and electrophiles. So if I flip this molecule around, this is basically HCN. And some of you have probably heard about cyanide. It's something you definitely don't want to play around with, but I want to use this just for example purposes, okay? So this is HCN, hydrogen cyanide. So now let's look at this molecule here. We just talked about it, that every line is essentially made up of 2 dots or 2 electrons. And what I want to show you is imagine I took the hydrogen and I pulled it off. Watch. Say I ripped it off. I took the molecule and I pulled it apart. Okay, I'm going to go back. Let's do that again. I'm just going to pull the atom off. Boom, just like that. So you can see when you pull an atom off or a letter, you leave the bond behind and those bond are 2 electrons. So let me just go ahead and twist this a bit right here. So now, what happens when we do this? One thing I want to point out is some of you might be saying, well, wait a minute, Jay, we did this example, and aren't there lone pairs on the nitrogen? If you saw that, yes, you are absolutely right. The reason I didn't put them on there is because I want us focusing on that carbon-hydrogen bond, because I'm going to show you why this is important in being able to see this. But you are absolutely right. If we drew the full-out Lewis structure, you would have lone pairs on there. You will find a lot of times that when professors draw these things out, as well as myself, we don't put all the lone pairs on there because we assume that you know they're there. We probably shouldn't make that assumption, I'll say for myself. But you are absolutely right. I just do that just to kind of make it easier. But the reason I did it here specifically is I was aware of that. I want you to look at the bond. So when we pull that off and we look at this, we did this Lewis structure, so you can go check this out. We know that that carbon is negatively charged because it has too many electrons. And we know the hydrogen over here has fewer electrons, so it's positively charged. Why is this important? Because you're going to see that any bond you break, basically when you is basically made up of a nucleophile and electrophile. Any bond you see, so when you start thinking about doing synthesis, you're like, oh my gosh, wait a minute. So if I break this bond, one of them has to be a nucleophile, one has to be electrophile. Which one's going to be what, right? So this is a key to seeing some of the things in organic chemistry. And so if I summarize this, we can see once we change the electrons around an atom, we change the charge of that particular atom. So if we think about negative charges act as nucleophiles, N and N, that means that atom has more electrons than, let's say, quote unquote, what it wants from the periodic table. Remember when we did Lewis structures, we figured out how many electrons are around each atom for it to be neutral. If it has more, it's going to be negative, which is a nucleophile. In this case, positive charges act as electrophiles, which means they have less electrons. So if we looked at that example, when we pulled the hydrogen off, no electrons went with that hydrogen. If you want, you can rewind it and watch it. We had no electrons going with the hydrogen, so it had less electrons, so it's positive. The carbon, on the other hand, when we pulled the hydrogen off, now it has an extra electron sticking to it, so therefore it's going to be negative. So it's that breaking and making bonds that allows us to find the nucleophiles and electrophiles. Now at this stage, you might be saying, oh my gosh, Jay, this makes so much sense. Now I understand why Cn minus is the minus, how to draw it, and then it's going to attack an electrophile. So the nucleophile makes complete sense, Jay. I really appreciate that, but hold on a minute. The electrophile, what about that? That doesn't, because if I look at that, I don't see any positive charge. It's just a structure, right? So let's talk about this. So I said before that essentially nucleophiles and electrophiles, I've said this numerous times, can be essentially, nucleophiles can be negative or partially negative. Electrophiles can be positive or partially positive. And what you'll find a lot of the times is that these things like, say, electrophiles are going to be partially positive. Now, how do we figure that out? Now, essentially, what I want to do is I want to take this functional group, and you can do this with literally any functional group that you are studying in organic chemistry. I'm going to show you how super simple it is to figure out how your functional group will react every single time. So in this case, this happens to be an alkyl halide, and in every single functional group, you're going to have two atoms that are most important. Remember this two that I talked about? 2 electrons per bond. You only need to know 2 things in organic chemistry, nucleophile, electrophile, and you have 2 atoms that you need to pay attention to in every single functional group. This 2, that is not a difficult number to know, right? Okay. So in this case, we've got a Br and we have a carbon. So this is an alkyl halide. That bromine could be a chlorine, that could be an iodine if you look at the halogens. But here we have a Br and we have a C. We want to look at those 2 elements, those 2 letters, and we want to compare them. How are we going to do that? Remember this handy dandy cheat sheet that I showed you? This from most electronegative fluorine to least electronegative hydrogen. We've got all the elements in between that we're going to see in organic chemistry, which is not a lot. So what we're going to do here is once we figure out what our function group is, we're going to take those 2 letters and we're going to highlight them in this chart and we're going to forget about everything else. How does this work? We can see that what this is saying is the element on the left is more electronegative. The element on the right is least electronegative. What does that mean? So when you have 2 elements and you have electrons in between, let's say these are electrons and here's an atom. If the atom is more electronegative, what happens is the electrons start to move towards that atom more, meaning that they're not specifically even between the 2 atoms. They're moving more towards the electronegative atom. What does that mean? If electrons start moving towards an atom, that's going to make that atom partially negatively charged. Not a full negative, but partially negative relative to the other one. When they move away from an atom, the other atom is now going to be partially positive. And it's this electronegativity difference where we get these partial positives and partial negatives that actually also allows, you'll find out, that allow molecules to interact and kind of do things. But basically what we want to do here is find out what's the most electronegative, what's the least electronegative, and we're going to think partial negative on the most electronegative, which is on the left, partial positive on the least electronegative, which is on the right, and then we're going to match that up on our electrophile. Or we're going to match that up on our alkyl, on our functional group. I'm just tripping over my words. So now when we look at this, we can say, oh, this makes sense, Jay, because now the carbon is partial positive, so that's going to be our electrophile. But some of you might be saying, well, Jay, how do we know that it's not the bromine? You said there are 2 elements to every function group, and you're exactly right. The thing here that's most important is, remember, carbon-carbon bond formation or bonds to carbon is the most important thing in organic chemistry. That letter C is the most important element. So what you are basically going to be doing in organic chemistry is creating bonds to carbon or breaking bonds to carbon. So when you look at a functional group, I want you paying attention to what is the charge or partial charge on your carbon atom, because that's the one that you're either going to attack or that carbon is going to attack, okay? So now when we go back here, we're like, oh my gosh, this makes so much sense now, Jay. I can see clearly the minus is the easiest one, right? That's a negative charge as a nucleophile. Now I know why it's attacking that specific carbon right there, because it's partially positive. So now you can see exactly, it's a carbon minus, that's our nucleophile. It's a carbon partial positive, that's our electrophile. Those 2 things come together like Legos, and we ultimately get this reaction right here. And what I want you to do is I want you to find other functional groups, and I want you to test this out, what I just showed you. You'll see it'll work 100% of the time. Now, I will tell you that if you happen to get to the alkenes, the double bonds, or the alkynes, triple bonds, you might say, wait a minute, Jay, this can't work because both elements are carbon. It's a carbon-carbon bond. It's the same electronegativity. How do you do that? Well, I'm not going to get there yet. We will get into that when we get to alkenes and alkynes, but I'm going to show you it does work. We just have to make a slight modification, all right? So that right there is an introduction to nucleophiles and electrophiles. We're going to go definitely into this and show you how to break every single function group down, but I wanted to give you kind of an introduction, all right? And so with that, I always enjoy getting to be on here with all of you. And until next time, I hope you all have a good one, and I look forward to seeing you next time.